Picture this. You're driving through traffic. You glance at your speedometer. It reads 60 kilometers per hour. But then, the red light flashes and you hit the brakes. Are you still moving at 60? Of course not. This is where average speed falls short. It doesn't capture what's happening right now. To understand what's truly going on in that exact moment, we turn to two powerful tools: instantaneous velocity and instantaneous speed. Let's start with something familiar: average velocity. It tells us how fast an object moves over a stretch of time and is defined as total displacement divided by total time taken. In formula form, v bar equals delta x divided by delta t, where delta x is the change in position and delta t is the time interval. Here's a quick example. A car travels from point A to point B, covering 100 meters in 5 seconds. So, v bar equals 100 meters divided by 5 seconds, which equals 20 meters per second. This gives us a basic overall idea of motion, but it doesn't tell the full story. Average velocity gives us the big picture. But what if we want to zoom in? What if we want to know exactly how fast an object is moving at a specific instant, say at t equals 4 seconds? That's where instantaneous velocity comes into play. It's defined as the limit of average velocity as the time interval shrinks smaller and smaller, approaching zero. Mathematically, it's written as velocity v equals the derivative of position x with respect to time t. This is what your speedometer actually shows, not your average speed, but your speed right now, at that instant. Want to see instantaneous velocity? Let's do it graphically. When you plot a position-time graph, the slope of the tangent at any point on the curve gives the instantaneous velocity at that specific time. For example, suppose the position of an object is given by x equals 0.08 multiplied by t cubed. Now, let's find the velocity at t equals 4 seconds. You draw a tangent line to the curve at that point. The slope of this tangent, that is, the rise over run, gives you the velocity at that moment. It's like zooming in on a curve until it becomes almost a straight line, revealing the speed at that instant with clarity. Let's now solve an NCERT-style numerical example using calculus to find instantaneous velocity. Suppose the position of an object is given by x equals a plus b times t squared, where a equals 8.5 meters, b equals 2.5 meters per second squared, and t is time in seconds. Spelled out, a equals 8.5 meters, b equals 2.5 meters per second squared, and t is time measured in seconds. To find instantaneous velocity, we differentiate position with respect to time. V equals dx divided by dt, which equals the derivative of a plus bt squared with respect to t, and that equals 2 multiplied by b multiplied by t. So the final expression becomes v equals 2 multiplied by b multiplied by t. Let's calculate the value of velocity at two different instants. At t equals 0 seconds, 2 multiplied by 2.5 multiplied by 0 equals 0 meters per second. At t equals 2 seconds, 2 multiplied by 2.5 multiplied by 2 equals 10 meters per second. So using calculus, we're able to find the instantaneous velocity. That is, how fast the object is moving at any specific instant. Now let's talk about instantaneous speed. While velocity includes direction, speed only tells us how fast. It ignores direction completely. Instantaneous speed is simply the magnitude of instantaneous velocity. Here's what that means. If your velocity is plus 24 meters per second, then the speed is 24 meters per second. If your velocity is minus 24 meters per second, the speed is still 24 meters per second. Speed is equal to the absolute value of velocity. So whether it's positive or negative, we take just the number. Also, keep this in mind. Unlike average speed, which can sometimes be greater than the magnitude of average velocity, instantaneous speed is always exactly equal to the magnitude of instantaneous velocity. So how do all these concepts play out in real life? GPS systems use instantaneous velocity to calculate your speed and direction at any given moment. Smartphones use motion sensors to detect tiny changes in your position and orientation. Engineers apply velocity time data to program motion in robots, drones, and vehicles. These concepts aren't just theory, they're part of the world you interact with every day. Now let's wrap up with a quick recap, starting with the formulas. 1. Average velocity. Average velocity equals delta x divided by delta t, where delta x is total displacement and delta t is total time. 2. Instantaneous velocity. Instantaneous velocity equals the derivative of x with respect to t, or in other words, how fast position is changing at a specific moment. 3. Instantaneous speed. Instantaneous speed equals the magnitude of velocity. It's always positive, with no direction involved. We also learned you can find instantaneous velocity graphically as the slope of the tangent to a position-time graph, or numerically using calculus by differentiating the position function. These tools help us analyze motion precisely, whether we're looking at a falling object or a satellite in orbit. And next up, we'll tackle acceleration, the rate at which velocity itself changes. Get ready to understand how things speed up, slow down, and sometimes even reverse.